For 4-6, we're looking at inverse relations and functions. So we're finding inverses, and then we're determining whether or not those inverses are functions. And we'll look at how I can tell whether the original is a function or not. So an inverse relation is formed when the roles of the independent and dependent variables are reversed. Remember that x is the independent variable and that y is the dependent variable. So they're telling us that we're just switching x and y. So if I have my original relation and I have a point xy, that means that the inverse will have a point yx. Okay, so if we look at an example of this, they've given it to us in a table. So I have this relation. This relation is a function. Remember, it's a function if none of the x values map to different y values. We'll see the opposite of that when we get to the end. So -2, 1 is a point, -1, 4, 0, 3, 1, 1 are all the points. So to make the inverse, I just switch my numbers in my columns. So x becomes 1, 4, 3, 1, and y becomes the -2, -1, 0, and 1. Okay, so I have the points 1, -2, 4, -1, 3, 0, 1, 1. So then after I switch those values, I want to reorder so that it's in order from least to greatest based on my new independent variable, based on my new x value. And so notice that there were two different ones, and because they map to two different y values, that tells me this is not a function. So if I plug in 1, I should know the answer and only get one value. That's how I know that it would be a function. So this relation is not a function. Okay, so let's look at this example a couple more times. So if I'm given a relation, so here I've got the table x is -1, 0, 1, 2, 3, 4, and then y is 9, 7, 5, 2, 3, 1, -1. So if I look at this, none of my x values are repeated. So I know that this is a function that I'm given. I have to figure out whether my inverse is a function. I'm going to write the inverse as a set, just so you can kind of see the different notations, because we will see it as a table and as a set. So I just want to have you see the connection there. So my inverse is going to be the set of points. So I'm switching the order. So my original point is -1, 9. So that means the inverse is 9, -1. Okay, my next point is 0, 7. So that means the inverse would be 7, 0. So I'm switching x and y. My next point is 1, 5. If I switch that, that will be 5, 1. The next point is 2, 3. So if I switch that, it's 3, 2. My next point is 3, 1. So if I switch that, it's 1, 3. And then my final point is 4, -1. So if I switch that, it's -1, 4. Okay, so remember that the best way to tell whether or not it's a function is to look at this in order by my x values. So in order from least to greatest, looking at the x values, my lowest x value is -1. So I'm going to write that first. So -1, 4 is my first point. My next, it looks like it goes decreasing this way, right? 1 is the next highest number. So if I go 1, 3, then my next highest x value is 3. And then 5. 7, and then finally 9. Okay, so what I can see from here is that all of my x's are different, right? -1, 1, 3, 5, 7, 9. So yes, this is a function. This is my inverse relation. So this set here this value here is my inverse relation. That is a function, so I could call it an inverse function. Okay, so then if I look at the next problem and do this similarly, right, I'm finding my set of my inverse. So I'm going to take each point here, so -2, 4, and switch the order of x and y. Oops, wrong. I wanted a parenthesis. Then I have -1, 1, so I'm going to write that as 1, -1, 0, 0. That one's nice because when I switch it, it's the same thing here, 1, 1. And then, oops, 2, 4. See, that tricked me because those are the same. So 2, 4, if I switch, is 4, 2. And then 3, 9, if I switch, is 9, 3. So remember that once we switch, we want to write it in order so that we can see if we have a function or not. So in order, our first point, our lowest x value looks like is 0. So I'm going to write 0, 0 first. Then I have 1. Notice I have 2 different 1s. So what this means is that if those are mapped to different numbers, which they are, one is mapped to -1 and one has a y value of +1. So because of this, that tells me that no, this is not going to be a function. Okay, so I'm not going to have a function. I want to finish writing it though, so that I have the actual inverse here. So my inverse is just a relation, not a function. Our next x value actually gives us the same problem. Look, we have 4, -2. And we have 4, +2. So both of those tell us that this is not a function because they have the same x, but different y values. And that's what tells us no, that they're not a function. And then our last point is 9, 3. Okay, so our inverse is a set of points 0, 0, 1, -1, 1, 1, 4, -2, 4, +2, and then 9, 3. Okay, so if you guys want one more practice, we can do the try it here on page 102. So visually, we're going to have to identify whether or not an inverse is a function. And so if an inverse relation of a function f is itself a function, it's called the inverse function. So we can't call it an inverse function unless it's an actual function. Otherwise, it's just called a relation. So we write f inverse as f with like a -1 power of x. So we read that as f inverse. So how can we determine if the inverse relation of a function is a function? So if we can say f inverse, and we do that by looking at the horizontal line test. So the horizontal line test is if I look at the graph of a function and a horizontal line only passes through the graph once, then its inverse is a function. Okay. If a horizontal line passes through the function more than once, the inverse is not a function. Okay. So this is called a one-to-one function that's going to pass the horizontal line test, meaning that every x value has a different y value. So the reason this one's not going to work is notice that this repeats, right? So because I have 2 equal y values that have different x's, that's what's going to tell me that this is not one-to-one. So if I'm told that a function is one-to-one, that tells me also that its inverse is a function. Okay, so what they did here is they're giving you the visual of the inverse. So they switched the values in the table and graphed them. So the dotted line is the original. And then the inverse is the one that's now solid. So notice it fails the vertical line test, which is the test of whether or not a graph is a function. So if it fails the vertical line test, it crosses the graph more than once, then that graph isn't a function. But because we know the way that this works, we can use the horizontal line test to check to see if something's inverse is a function without having to actually graph the inverse. The question doesn't ask us to. Okay, so for this example, we're going to do all the graphs first and kind of talk about how that's related to the horizontal line test and what we did with the table and switching X and Y. So we're going to kind of go out of order and just do the graph part of each of these and then come back and do the algebraic part. So for example 2, we're finding the inverse relation and determining if it's a function. So we just talked about the horizontal line test. If I take my equation, so my equation's over here, this is my problem, f of x equals negative 3x plus 5. So I got that from this guy here. I don't know why it's not written over there. Okay, so what I want to do is I want to think about the graph of this. So I see that x is to the first power. So I know that this is linear. Okay, so if I have a linear function, my slope in this case is negative 3. Remember, we write it over 1 if it's not a fraction so that we can do rise over run. My y-intercept is the constant, so in this case, 5. So if I want to graph this function of negative 3x plus 5, I'm going to put my y-intercept at 5. So that's the point 0, 5. And then I'm going to do my rise over run. So I'm going to go down 3 over 1, down 3 over 1, down 3 over 1, right? So I can do that until I fill the graph. And that will create my straight line. And my drawing's not going to be great just because of how I'm doing this on the screen. Okay, so that is the graph of negative 3x plus 5. So what we talked about with the horizontal line test is, so if I look at this, I know that my function, my inverse is a function if this graph passes the horizontal line test. So if I draw horizontal lines, they should only cross the graph that I drew one time. And so notice that that's the case for a line. And so this function, so f of x passes my horizontal line test. So when I do this final step and I find my inverse, I am able to call it f inverse. Okay, so this will be an inverse function, not just an inverse relation. I wanted to look at what the inverse looks like in terms of the graph, though, so we can talk about something else. So if I think about this, what we learned in the previous problems were that I guess this one's fine, is that I switch the values of x and y to find the inverse. So once I have the graph of f, I can switch the values of x and y and use that to find the inverse. So this point, my first point, I'm just going to recreate this back into a table, is the point 0, 5. So what does that mean for my inverse? That means that a point on my inverse would be 5, and then the y would be 0. So I'm going to have the point 5, 0 on my inverse. If I go back and look at my graph, the next point was 1, 2. And then I'm going to do one more point just for extra. And then, so then I had 2, negative 1. Okay, so if I take and I switch those order, I get the point 2, 1 and the point negative 1, 2. So if I graph those, the point 2, 1 is here, and the point negative 1, 2 is here. Okay, so the inverse function is actually also a line. So the black one that I drew was f. This new blue one is its inverse. And again, I can see that it's a function because if I were to do the vertical line test, it would pass. Okay, so one thing to note about the graphs of inverses is that there is this line. I'm going to do it yellow. Let's see if I can draw this correctly. Oops. The line y equals x, for which this is reflected across. So every point on the graph of f gets reflected across the line y equals x when I switch the order of those values. Okay, so let's look at the graphs of the other functions before we talk about how we find the equation of these lines. So the next problem, I have f of x equals the square root of x minus 2. So if I go ahead and think about that, that's a square root function. Remember, a square root function looks like this. So when I do a square root function, I need to think about it as a times the square root of x minus h plus k. And so that tells me that here my a is 1, my h is 2, and my k is 0. When I make the table for this, remember that h and k is our first point. And then to get our consecutive points, we add a on the y. So I'm going to add 1 twice to get my next 2 y coordinates. And then remember that this was the inverse of a quadratic. So I add odd numbers to get the values on the left. So 2 plus 1 is 3. 3 plus 3 is 6. So that means that my graph for this will have the points 2, 0, 3, 1, and 6, 2. So that's going to be the graph of f. Remember that it will be reflected across the line y equals x. So across this line here, when I make my inverse table. So the inverse function of this, I'm going to draw it over here using a different color. If my table was this, I'm going to take and switch the x and the y coordinates. So my first point 2, 0 becomes 0, 2, which would be here. Notice it's reflected across here. If I think about that reflection, that would mean my next point should be here, which is 1, 3. Notice how that worked. 6 would be here. So if I reflect 6 across, it looks like it should be here. And I can double check that if I switch the order to 6. Notice that, oh, I was off. 2, 6 would be there. So then that means that the inverse would be this. So we think back to the horizontal line test. If I were to draw horizontal lines through F, I could see that they would only touch F once. So this passes that horizontal line test. I know this is your margin, so I'm trying to write small. So it passes the horizontal line test. So that means that I can write this as f to the negative 1 of x. Okay, so I can, it is in, the inverse is a function. Okay, so let's look at one more example of this before we go back and find the equation of these. So remember that the fact that this passes the horizontal line test tells us that this function passes the vertical line test. And so I know that since this passes the vertical line test, that value, that graph is a function. Okay, so last one we've got f of x is x squared minus 9. this is a quadratic. So remember that the standard or vertex form of a quadratic is a times x minus h squared plus k. So looking at this, our a is 1 because there's a 1 in front of x squared. Our h is 0 because there's nothing inside the parentheses. And then our k is -9. So remember that tells you where your vertex is. So our vertex is at 0, -9. And then since a is 1, it's an up parabola with the pattern 1, 3, 5, and so on. So let's graph f. So we're going to plot the vertex 0, -9. Of course, it's not on here. So 7, 8, 9, we'd say is about there. And then if we go out 1, up 1, we're going to be here. I should probably make a table. Let's make our table here. So for f of x, our x and our y, remember that for a parabola, the vertex goes in the middle. And then we want 2 points on either side. So we just found the first set of points. So that would be 1, -8, and -1, -8. If I look at those coordinates. And then after I go out 1, up 1, I want to go out 1, up 3. So I would be at those 2 points. So at -2, -5. And at 2, 5. So this would be the graph of f. And then I would look at this to tell if its inverse is a function. So if I think about the horizontal line test, if I were to draw a horizontal line, notice that it will intersect f twice, more than once. So it fails the horizontal line test. So that means that the inverse is not a function. So when I write my inverse, my final answer is just going to be a y equals, okay, because that is not a function. If I take and find my inverse now, so I'm going to take my table and switch my x and y values. Remember that I should end up with a graph that is reflected across that line y equals x. So my graph, my point should be reflected across this. Is a way that I can check that I did it correctly. I'm going to squeeze this into the margin. So my inverse is going to be the points -5, -2. So -5, -2. And that's that reflection. And then the next point is -1, 8. So -8, -1. And I messed up and put my so this would be -7, -1. So it would be here. It would be in my table. And then 0, -9 is going to turn into -9, 0. So it would be about there. And then my next point, 1, -8 is going to be -8, 1. So see how now it's not a function. This is what's the problem is. I plug in -8, I get 2 different answers. This graph won't pass the vertical line test, which I saw from its inverse. And then finally, our last point is 5, 2, if we switch the last point from this table. So -5, sorry, -5, +2. I wrote that as a positive there. Okay, so this graph is the inverse. Okay, so again, notice that it does not pass the vertical line test because the original graph didn't pass the horizontal. Okay, so that is the graph of an inverse. So I can create a graph with an equation, switch the x and the y values, and that creates the graph of the inverse. It is always reflected across the line y equals x. my inverse is not a function if a horizontal line crosses the graph of the original problem more than once. So B here was the only one that we saw that failed that for horizontal line test. So if I look back here, if I have a horizontal line that goes through anywhere on this, it's always only going to intersect once. And the same thing happened with this linear function, right? All the horizontal lines only intersected that black line one time. Okay, so that's looking at this graphically. We're going to do this algebraically to determine our answer. So notice that our graph, the blue graph, is what we're going to figure out the equation for, is also a line. So I know that I should get a linear problem, a linear equation as my answer. Our first step to solve an inverse algebraically is we're going to rewrite f of x as y. So we're literally just going to change this to a y. So y equals negative 3x plus 5. Okay, then we're going to switch the roles of x and y. So in my equation, y is first, so I'm going to make x first, and x is second, so I'm going to turn that into a y. Everything else is going to stay the same. So x equals negative 3y plus 5. Next, I'm going to solve for y. So this is the bulk of the work. So I need to isolate my y. I'm just going to rewrite my equation. And I'm looking for this to be isolated. So since it's being multiplied by negative 3 and added with 5, I want to undo the 5 first. So I'm going to subtract 5 from both sides. Notice that I cannot actually subtract 5 from x. So I just write that as x minus 5 is equal to negative 3y. Sorry, that got a little messy. Then, in order to get the y by itself again, I need to get rid of the negative 3. I'm going to do that by dividing. So if I divide both sides by negative 3, that gives me that y equals, and technically I have this x minus 5 over negative 3. I want it to look like this because that's what linear functions look like. So I'm going to simplify. Remember that if each term is divided by that value, I can split my fraction. So I have x over negative 3 minus 5 over negative 3. And I'm going to kind of go over here and do some work there. Remember, if I think about that, if I just have x, it's like I have 1x. So I have really negative 1 over 3x. If I take that away as a coefficient, so that's my m, right? My slope is negative 1/3, which I can see here, right? I go down 1 over 3, so that looks good. And then this, I have negative 5 divided by negative 3. I'm going to leave that as a fraction, but since I have negative divided by a negative, I'm going to turn that positive. So I got that y equals negative 1/3 x plus 5/3. If we think about 5/3, that's 1 2/3, right? So my line's not great because I drew it kind of above those points, but notice it looks like it's going through 2, but if I had connected those points better, it would have gone through 1 2/3. Okay, so that is my equation of the line that I graphed. Because remember, the original line, the black one, passed the horizontal line test, the linear function passed the horizontal line test, I'm allowed to change my y to f inverse. So I'm going to rewrite it as f inverse of x equals negative 1/3 x plus 5/3. And that is the answer to this problem. So that is an inverse. That is my inverse function. Okay, so let's look at the square root function. So for this problem, we've got f of x is equal to the square root of x minus 2. We're following the steps that we just took to find this inverse. So I change f of x into y first. So I have y equals the square root of x minus 2. Then I switch the roles of x and y. So I get x equals the square root of y minus 2. And then I have to solve for y. I'm going to rewrite this just so I can see the steps separately. So in order to solve for y, I need to first get rid of the square root. So to undo a square root, I have to square both sides. So I'm going to square both sides. That's going to give me that x squared is equal to y minus 2. Then if I want y by itself, I'm going to have to move over the 2. So I can move the 2 over by adding 2 to both sides. So that gives me x squared plus 2 is equal to y. Okay, we already said that our graph passed the horizontal line test. So because of that, we're able to rewrite our y as f inverse of x. And then that is just equal to our x squared plus 2. So notice that our answer is quadratic, but our graph is only half of a quadratic. Okay, and that's really just because when I start with a square root that has a set domain, remember that it's this has a domain from 2 to infinity and a range from k to infinity, so 0 to infinity. And so when I switch x and y values, that switches the domain and range. And so this one ends up with a domain value of from 0 to infinity. So we aren't going to have that as part of our answer. You might in a higher level math class, but that's why I have an x squared function. It doesn't quite look like a parabola. Okay, so for the last one, we've got an x squared function. So if I think about these two as opposites, right? I was given a square root and I got, a squared as my answer. I am given a squared, so I should end up with a square root as my answer. And again, we can see that our graph doesn't quite look like a square root function, but we'll talk about that once we've solved. So for this one, let's rewrite our equation. So we have f of x equals x squared minus 9. Remember, our first step is to change f of x into y. So y equals x squared minus 9. Then we switch the roles of x and y. So x is going to equal y squared minus 9. I'm going to rewrite again just before we solve. So x is equal to y squared minus 9, and we want to isolate the y. So currently, it's being squared and the 9 is being subtracted. Remember, we work from the outside in, so we're going to add 9 first. Since we're adding 9 to x, we can't actually combine. We just get x plus 9 is equal to, that canceled out, we have a y squared. To get rid of the square, we have to do the square root. Okay, so we have to square root both sides to get rid of the square. Remember, whenever we take the square root of a variable squared, we have to write plus or minus on the other side in order for this to be true. So we have plus or minus the square root of x plus 9 is equal to y. So remember that when we graphed a square root function, it looks like that. So the minus is giving us that bottom half. That's where this part of our graph is coming from. So this is the plus and this is the minus, and that's why our graph looks like that, which is why failed the horizontal line test originally because our graph of the parabola was not one-to-one. So it's not a function, which is why I wrote that box with the y equals. So we're just rewriting this equation in the correct order. So y equals plus or minus the square root of x plus 9. Okay, so that is finding the inverse. Those steps in example 2 are what we followed for each of these. Remember that the graph is always reflected across the line y equals x.